You're going to find out that we're doing today and really for the next week or so is kind of the second half of this chapter. That is the application of graphing. Now, as soon as we say application, people think word problems. Well, it will be word problems. But before we do the word problem side, we're going to be looking at more of a math application. A lot of it's going to be notation. Okay, it's going to feel a little mathy. It's going to be some interpreting notation, understanding what it means. But it's part of the application, and then we will get to the word problems, which don't have to be such a, oh no, word problems. I find that kids actually, if you're motivated by understanding how math connects to the real world, you'll find out that there's some really neat connections, ultimately with like a sine wave and, again, the real world. Now, to start off today, I want to pose to you these three statements. They have some notation in them, and they are saying something. You can jot them down if you want, or you can just look at them. But my question to you is, what do you think is true? What do you think is true? We have this statement that says that the sine of x equals a half, and then there's a statement that says x equals the inverse sine of a half, and then there's this statement that says x equals arc sine of a half. Okay, welcome to the notation. But what do you think is true? Now, if you're thinking, that's good. And if you're thinking that they're all the same, you're correct. Okay, now if you weren't sure, that's fine, but I'm kind of telling you that all three of those statements are essentially saying the same thing. And what we want to do today is, as it says over here, we want to learn how to interpret these and solve them. We're going to interpret and solve, and you'll find out that each of these is known as inverse trig notation. Okay, now if we want to interpret, we kind of have to understand what the sine of x equals a half is saying. And if we want to solve it, then we want to find x. Okay, now it's kind of interesting because if you're thinking, is there a trick to this? I feel like that, I've solved something like this before. Well, you're right. You have solved something like this before. And maybe we could say that there's not a trick to that, because if I asked you to solve that for x even weeks ago, I would hope that sooner than later you would say, hey, I can just do the inverse of both sides. I can do the inverse of a half, and out pops 30. And honestly, on one level, that is what's going on here. That is x. X equals 30. Okay, now remember that to say that x equals 30 is to say that the sine of 30, I kind of follow the bouncing ball here because now I'm taking my answer and I'm plugging it in for x, and that means that the sine of 30 equals a half. Now this isn't supposed to be kind of like blow you away. This is just helping you realize that this is still true. Okay, but if you look at what I've done up there, you should say, well, yeah, you did the inverse sine of a half. You did x equals the inverse sine of a half. And as we said a couple moments ago, all three of those statements are the same. So we have two statements that are the same. We'll get to the third one in a moment. You know that 30 is not the only angle that equals a half. Another way to say that is 30 is not the only x value. Say what? Well, if you mess around a little bit with angles, you might encounter 150, where you find that also equals a half. Now, the real question is, how do you get that? Because if you're paying attention, you would say, well, you just kind of plug that number in. How am I supposed to know that it's 150? If I do it on my calculator again, I'm not going to get 150. I'm still going to get 30. And so we kind of get to the next phase of this little conversation where we're trying to interpret and solve these statements. Now, go back to the original statement, the sine of x equals a half. Okay, most kids kind of feel most comfortable with that because you've seen the sine of x. You've seen it as a graph. And what I want you to realize is that to say the sine of x equals a half is also to say that the graph equals a half. What do we mean the graph equals a half? Okay, well, I'm talking about the graph of the good old sine wave. Now, you can play along if you want. You can just kind of watch because I'm kind of going through a little intro here. But make sure you realize what I'm doing. I'm now suggesting that we could say the graph equals a half. Okay, now you're going to see again the sine wave. You've seen it a number of times, and you guys have really grown a lot in the last few days. But now we kind of look at this graph in a little different way. We want to look at it and say, when does it equal a half? In other words, when does the y value equal a half? Now look what I did. I just traced until the y value equaled a half. And maybe it's not a big surprise to you that that's happening at 30. Are your eyes already looking over to the next place where it equals a half? Now, when I say equals a half, I mean the y value equals a half. And you end up with our 150. You end up with the other angle. Now, something's happened here. It's kind of like a different way to look at these graphs. And even though you might not draw on your calculator, what I've really done is my eyes have kind of gone to that place of a half and tried to pick out those 2 points, those 2 angles. Okay, and you'll learn in a moment that what I used there was the graphing method. Basically, the graphing method helps us to solve these statements. Now, the last statement that was written back there, it said the arc sine of a half. It read the arc sine of a half. Back in geometry land, arcs on a circle. Are you picturing that for a moment? An arc on a circle. It's like on the outside of a circle. An arc is the same as an angle. An arc is an angle. That was something that always kind of confused me in high school. Maybe I wasn't paying attention. I was making it too tricky. But an arc is the same thing as an angle. And what I want you now to realize is that all 3 of these statements are referring to angles. And that's kind of our big idea for this somewhat strange lesson. And that is that whenever you have an inverse, it's always an angle. I'll let you process that if you want to jot it down. So inverse trig notation. Honestly, today's lesson is always referring to an angle. And I'll make sure you realize that even by the example I did, that it could be more than one angle. Okay, if you're kind of like, how do you know if it's like more than one? Okay, we'll keep talking about that. But I just want you to realize that these 3 statements are all referring to angles because they're inverses. Okay, and an inverse is an angle. Now, just the same that an arc is an angle, and even our original statement is technically referring to an angle as you solve it. How about this kind of mathy statement? X equals the arc tangent of -1. X equals the arc tangent of -1. Now, I hope just from the 5 minutes we've had so far that you say, okay, that's an inverse statement. It is. It's an inverse statement. It uses this word arc. Arc is the same as an angle, and angles are the same as inverses. So the answer to this problem is an angle. Now, to find the answer, you very well could think of it literally as the inverse. So understand that whether I wrote the first thing on the board or the second thing on the board, it really wouldn't matter, again, because I'm trying to find that angle. Now, here's sometimes the part where kids are like, am I allowed to do this? Yeah, you can do the inverse of -1. Okay, now I hope that you realize that when you do that, you're finding x and you're finding an angle. But you'll notice that I keep putting this comma after my answer. And honestly, the reason I keep putting the comma after the answer is because these two statements and their triplet here, their little third statement, can all be used to find some more angles. Now take a look what I wrote here in this third statement. Okay, sometimes people aren't real comfortable, like, you're allowed to just write that. Yeah, I kind of took the inverse back over to the other side. So I can think of it as just a regular tangent. Now I'll tell you, after the lesson's over and people are like, I think I got this, this is like the number one mistake, that people still graph the wrong thing. What do you mean the wrong thing? Well, basically people try to graph the inverse. Please look carefully at what I have typed in the calculator. I am not graphing the inverse. I am graphing a regular tangent so that I can see when it equals -1. Okay, you're always going to graph the original equation. Okay, because the thought here is that it's kind of like asking, when does the graph of tangent equal -1? I just want to give you a second, if you're playing along, that maybe you can try to find an answer. If you're just kind of looking at my graph, where are you looking? Okay, again, it's kind of a little different way to use these graphs. You should be looking at -1. Now, when I say looking at -1, I mean looking at the y value of -1. Drawing that line might help. Your eyes need to go to these places. Now, this spot right here was the one that we seemed to find when we used the calculator. But how about this spot? Okay. Make sure you can trace. Sometimes people are, how do you, just trace to the right. As you trace to the right, the spider eventually gets to 135. Okay, so we have 135. How far away is that last point? How far away is it from 135? We could trace there, and maybe I'll beat you if I start tracing, but how far away to that next point? Yeah, so can we use some skills, some knowledge from the last few weeks to be able to say, oh yeah, of course, that's going to be at 3:15. Okay, can we add a period? The answer, of course, is yes. Okay, now, at this point, I want you to realize that each of these statements are the same. We can solve them using somewhat of a myriad of methods, but the main method we used is to graph. And just by the way, as you guys keep taking math courses and the teacher does stuff with a graph, never a bad idea to sketch it. It all depends on what you need as a student. But if I do something up here, you can always reproduce it here. And if I can help you reproduce it, I'm trying to just show you that we basically looked at -1. And again, it's your notes, but this is a common way to sort of show your work, or at least to remember what you did. So let me reproduce that. We could reproduce the sine wave up here and see those intersection points at 30 and 150. Maybe you're saying, sounds good, but how do I know how many answers? You had 2 answers for this. This one looks like maybe we have 3. Couldn't the answers go on forever? Okay. The answer to that is yes, they could. So we sort of make up a little bit of a rule of thumb. And the rule of thumb is that when you use a graphing method, you will contain your answers between 0 and 360. I'm going to erase one of the answers up here, but I just want you to realize that we will restrict our answers from 0 to 360. That way we're not basically listing answers forever. Now look at what I wrote up here. It's trying to help you see simply how to use a graphing method. And although you might not realize why I'm saying this, I'm just telling you it's a common mistake that students graph the wrong thing. Okay? They graph the inverse. But what I'm trying to suggest here is you just graph the good old sine, cosine, or tangent. Even if the notation looks fancy, you always graph just good old sine, cosine, tangent.
So if we put negative 45 degrees, would we have that correct if it's not within the boundary?
I'll be honest with you, I'll probably not make a big deal out of it as long as you have listed all the answers within the sort of the domain here. But I am going to erase this now, or at least cross it off just technically because I said 0 to 360. But listen, the real truth is the list could go on forever because I hope you realize that these graphs from the last week or so are periodic and they repeat themselves. So we just kind of say, hey, just list 0 to 360 so that you don't have to list numbers forever. Try one. I've given you a little bit to think about, but want you to see if you got the idea. Okay, now if you would see this problem on a homework or on a test or quiz, the directions would say interpret and solve. Okay, so you have this statement, you're trying to interpret it, and ultimately you're trying to solve it. And feel free to kind of tinker around with the skills that I've shown you.
I don't like calculators that much, but whenever I do the trace, it always starts with like x equals 0 and y equals 470 million. What do I do? And then it goes by hundreds.
You're tracing a scatter plot. There's like data in the calculator. Maybe it's just accidental, but if you turn off those plots, then that weird background scatter plot will be happening. When you push the trace button,
Should actually,
it'll be tracing the cosine.
Oh, that's so much better. Oh, well.
And right now you're just kind of moving a crosshair around the screen. So you trace button attached to the screen, attached to the graph. How's this going? I kind of gave you a problem that required a little bit of adaptation. It looks good though. I'm glad to see what you're doing. Work out some of the kinks. I saw some people do this. Just to be clear, you don't have to do that, but you might want to think that way. Like you might want to think, oh, just cosine. Okay, in other words, you graph the cosine. Again, you don't have to do this. Most people actually don't, but for some reason, if arc cosine had been written on the board, nothing would change of what we're going to do. So all three of those statements are the same, and they refer, of course, to an angle or angles. Now, if you were kind of like, do I need to know what root 3 over 2 equals? Yeah. Okay. It's not like you have to have that memorized, but I would say you need to find out that it's 0.86 so that you can trace to, well, 0.86. Okay. Now, there's one of the answers at 30. Okay. What I was kind of wondering, although I can't see in your head, but did your eyes say, hey, over here looks like another place where that's going to happen, kind of like on the other side of the valley? Now, be careful. This point over here is not a full period. That would have been kind of neat if we could just say add 360, but it turns out that that's not exactly true. But I'll show you in a second what is true about that point, and it does have something to do with 360. But anyway, it comes out to be 30. I'm sorry, 330. 30 and 330. Any questions? Anything? Because on one level, this is it. These are that you interpreted and solved it. On another level, there's something going on here that kind of takes us to the next step, and that is simply something that involves triangles. This is trigonometry, and might be able to argue that eventually everything kind of goes back to triangles. Actually, everything kind of goes back to the unit circle. But if I was going to interpret and solve this problem thinking about triangles, you'll find out in a second that we could pull an idea from first couple weeks of school. Now I'm going to use this version just because it's a little easier to say that if the cosine is equal to root 3 over 2, that would mean that x and r are equal to root 3 and 2. Okay, so x and r are equal to these two numbers. Now what I'm doing here is appealing a little bit to some prior knowledge where a student might say, okay, that means that we're talking about a triangle with a certain kind of x value, namely a positive x value. Now, where are triangles with positive x values? Well, a triangle that goes out to the right and continues to sort of triangulate, basically make a triangle, would suffice. If we start filling in some other numbers, everything's still fine. My main premise here is that we're trying to find triangle with a positive x value. Are you feeling like there's another one? Okay, you should be. At the time, you were really good at it. So let me hopefully affirm to you that that triangle right there also has a positive x value. Now, what I hope to show you is that this triangle method, in a moment we'll officially call this the triangle method, but that this triangle method is able to produce the same angles. It's able to produce the same angles. We're just a step or two away from that. Okay, you might feel like that you want to fill in some other information on these triangles, which you should. It's a special triangle. It's of the form 1, 2, root 3. So the y value is 1. This y value is technically -1. It turns out, though, that what's most important is the angles in these triangles. Now, the reason that the angles are most important is because today's lesson is all about angles. And you should know the value of either one of those yellow angles. Okay, they would both be 30. They would both be 30. Are you ready? We're ready to make a connection. Now, the cool thing about this problem is we already know what the answers are, 30 and 330. Okay, but how to get them from this triangle method? Listen carefully. You rotate to the terminal side. What do you mean the terminal side? Well, the first triangle's terminal side is right there. And so the question becomes, what does it take to rotate to that position? Well, the answer, of course, is 30. How about the other terminal side? This one requires a little more rotating. I'm going to draw here because I want you to see where I'm rotating from. Did you see where I started? At 0. And interesting, I almost rotate a full 360, right? Of course, it's 30 degrees shy of a full 360, and that's why we say 330. Now, this is an interesting spot in sort of your growth as a trig student. I know this might be not the most exciting lesson ever, but it is kind of interesting because what just happened here on this graph, on this sketch, is the same thing that happened on that graph. Okay, because both of these represent angles. Both these represent rotations. One of them was just a graphical representation of rotating to 30 and then rotating out here to 330. And one of them was more of a triangle representation. Okay, they both represent the same idea, angles. This is a triangle method. I find actually kids sometimes prefer this method, I think because you're finally kind of getting it. But let me expound a little bit on the triangle method. It's actually something that you've done before, but it doesn't hurt to kind of just see it again. I have just a kind of a little phrase or a couple phrases. You're going to sketch the triangle. That should be or could be plural. So maybe you want to say sketch the triangle or triangles. So you sketch the triangles. And then you determine the rotation. You determine the rotation to the terminal side. Okay, so the triangle method is another way to think about angles. You're going to feel a little bit more like you're thinking about angles from triangles. And when you're ready, we can ponder this last problem here. We've got the arc sine of -1/√2. Now again, it's kind of a mathy statement, all right? Let's just be honest. You're trying to interpret it. I hope one thing you got from this lesson is that to interpret that statement is to realize that it's simply inverse trig notation, which really just is a fancy way to say we're trying to find angles. Some students find it much more helpful to rewrite it. And I want you to be comfortable doing that. Like, there's nothing wrong with me looking at this statement and saying, okay, that really just means the sine of x equals -1/√2. You don't have to rewrite it. Okay, because no matter which way you think of this problem, whether the way I gave it to you or this way, I kind of prefer this way. As you can see, it's talking about the parts of a triangle. Okay, now it's still like the sine, and I think I had said a month or so ago, don't forget those definitions. And we'll kind of review them again, but it's talking about sine, so that means y/r, right? In case maybe that slipped your mind, but we're basically talking about a triangle that has a negative y value. Of course, the negative goes with the y, and then an r value of √2. It doesn't hurt if you want to think about this. If you would rather wait for me, I understand, but I'm just giving you a chance. Can you sketch a triangle with a negative y value? I mean, ultimately, that's kind of the thinking behind this problem. Can you sketch a triangle with a negative y value? And okay, now sometimes students will ask, honestly, how'd you get that? My best answer is those are the two triangles that have a negative y value. Okay? You always draw the triangles in this manner. That is, you always draw them where the terminal side comes back to the origin, and then of course your legs are in these positions. Now you kind of have to know where this is headed. What I mean by that is that you have to know that this is headed to a special triangle. So I'm filling in some other numbers, like, hey, this is a 1, 1√2. So yeah, you got to know that that's a special triangle, 1, 1√2. And quite honestly, what you really need to know is that these angles in here are special, because in a 1, 1√2, these angles have to be 45, right? So if you're like, is it -45? Well, that actually doesn't matter. This is what matters. And this is the part where sometimes kids are like, how do I get the answer? Love for you to be able to get this. That's why I'm going slowly through it. Check this out. You just have to rotate to the terminal side. Like, you just have to say, how far is that? Now notice I started at 0, but I'm confident that every one of you knows that that's 45 degrees past 180. That's exactly what's going on here. 45 degrees past 180. And then your other one, now go back to 0. Go back to 0 and rotate almost 360 degrees. Of course, 45 degrees shy of that. Okay, so our two answers are 225 and 315. Okay, so notation referring to angles, whether the angle is on a triangle or whether the angle is on a graph. We want you to get to the point that you realize that it's all the same. And so just kind of one last thought on this problem here. We had a sine, okay? We had a sine wave, but look what we were really doing. We were finding when the sine wave is equal to -1/√2. Now, -1/√2 is a negative y value, and that's happening at these two angles, again, which are 225 and 315. Okay, so you got some stuff to kind of think about. There's two methods. Your homework helper tries to get you to do both. You want to be able to do both. Sometimes kids are like, can I just do one? I want you to know how to use a graphing method and a triangle method. And again, your homework helper will give you a chance to practice that.